All right, so remember that we have previously studied the mean value theorem for derivatives. This time we're going to be focusing on the mean value theorem for integrals. So take yourself back to the mean value theorem for derivatives. It said that if the function is differentiable, which means it must have been continuous, on the closed interval from a to b, then there exists a point C such that f prime of C is equal to f of b minus f of a over b minus a. So the slope of the tangent was equal to the slope of the secant. Mr. Lakin found this joke. Your mother was a hamster and your father smelt of elderberries. This is from Monty Python and the Holy Grail. Not really sure what this does in relation to calculus other than the cartoon is cute. So now for the topic. The idea for the mean value theorem for integrals is this. Given a curve with a particular requirement on a to b, okay, so a closed interval, as most of our theorems are revolved around, you need to construct a rectangle whose area is equal to that of the area under the curve. So, in other words, if f is integrable, mean value theorem for derivatives said f was differentiable. This time we're saying f is integrable, which means we can take the integral or the antiderivative on the closed interval from a to b. Then there exists c on ab such that, drum roll please, the integral from a to b of f of x dx is equal to f of c, remember c is that magic value, times b minus a. And you might be thinking, Ms. Schwartz, what? Let me explain. This side, the integral from a to b of f of x dx, hopefully we can all agree, is this pretty green area that's underneath our curve from a to b, with this being our function f of x. What this says is that there will be a magic rectangle whose width is b minus a, the distance here in blue, and whose height is equal to f of c. And what's important about this magic rectangle is that the area colored in red is exactly equal to the area that's colored in green. And you can kind of picture it, right? Like this green has a little more up here, but the red rectangle has a little bit too much in here. So it's like this green stuff poured into this part. So f of c is the height. C is where that magic height occurs. Take a second, see if you can summarize the mean value theorem for integrals in your own words, but make sure that you set up the condition that your function is integrable. Go ahead and pause your video, jot something down. All right, so this is kind of what I came up with. You can pause and read that more if you want to. I prefer that you don't just steal my answers because, you know, copyright and such, but if you're looking for some inspiration, there is your inspiration. Okay, so we're going to switch gears a little bit. We're going to transform here in a second. And we're going to talk about the mean value theorem for integrals and how it relates with something called the average value of a function, which is often used in real-world applications all over that AP test for sure. So pause for a second and see if you can write out the statement part, or sorry, the reason part, the conclusion part of the mean value theorem. So pause and see if you can write it, or maybe just flip back to the bottom of the graph on the last page and write that statement instead. All right, so we know that the green pretty area that is underneath the curve will be equal to a magical rectangle that has a height f of c and a width of b minus a. So watch this next part. We are going to transform by looking and isolating just the height. So to isolate the height, I'm going to divide by b minus a. Dividing by anything would be the same thing as multiplying by 1 over. Ta-da! Transformation. So if f is integrable on the closed interval from a to b, then the average value of f is equal to 1 over b minus a, the integral from a to b, f of x dx is the average value. So the average value is f of c, which was the magic height of that rectangle. Okay? Magic height is the average height of that rectangle, the average value, the average height. When you look at this, hopefully you're saying average makes sense because I'm summing a bunch of stuff and then dividing back by something. Well, how do you find the average in mathematics? You add up a bunch of things and then you divide back by the number of things that you have added. So before we do an example, consider the following. The average value states that if f is integrable, then this statement is true. All we did was move the b minus a underneath, okay? And this was our part in green, equals that magic height. Well, we know, though, to do this part in green, we would take the antiderivative and plug in b minus the antiderivative and plug in a because of the fundamental theorem of calculus. Okay, well, looking at this looks awfully familiar. This to me looks like the slope, more specifically the average slope of capital F. Wait a second, this is getting too weird. Is equal to little f of c, but we know that little f is equal to big F prime. So the average slope of f is equal to the instant slope of big F. What? What? This is the MVT for derivatives. It's almost like it was planned that way. Okay? What's important, though, is really the average value. That's what we're going to use the most often. Anytime you look to find the average value of something, the average value of f is this expression right here. Okay? So let's try 2 problems. They'll go pretty quick. Find the values of c guaranteed by the mean value theorem on the interval 1 to 3 for this function f. So I'm going to look for the value of c. That is my goal. I'm going to start just by writing the general mean value theorem. Mean value theorem says the integral of f of x dx from a to b is equal to f of c times b minus a, and c is the thing that I'm looking for. Okay, so let's set this up. I'm going to integrate from 1 to 3. I know I'm going to need to rewrite this as 9x to the negative third dx equals, well, f of c is going to be 9 over c cubed. And then b minus a, the width of my rectangle, is 3 minus 1. Okay, thinking about my antiderivative here, this is going to be 9x to the negative second divided by negative 2, evaluated from 1 to 3, equals 9 over c cubed times 2. Finishing out the left side, I would plug in 3 minus plugging in 1. All of that is still equal to 18 over c cubed. I'm running out of space, so I'm going to jump over here. Thinking about this then, I'm going to end up with, on the left side, I believe I come out with 2, if you type that all into your calculator, equals 18 over c cubed. Oh, just kidding. It's 4. Checking my notes. It's 4. So then I get 4 c cubed is equal to 18 c cubed is equal to 9 halves, and c is equal to the cubed root of 9 over 2. So c is where the magic height occurs. The magic height itself would have been equal to 2, okay? Because the left side would have been 4, and back up. The stuff in green was equal to 4, and that would have been equal to 9 over c cubed, the magic height, times 2. Okay, so the magic height was 2. Thinking back to the graph, let me just scroll back here. So what we just found is that c was the square root cubed root of 9 halves, and that our magic height was actually equal to 2. So c is where it occurs, f of c is the magic height. Last one, find the average value. So the average value this time is the magic height of the rectangle. So we want to use our isolated formula, 1 over b minus a. This, by the way, is going to be the one that you use way more often. Oops, keeping it general for now. Equals f of c, and this is the whole thing that we are looking for, that height of the rectangle. So I'm going to take 1 over 4 minus 1, the integral from 1 to 4 of 3x squared minus 2x dx, and all of that will be equal to f of c, my magic height of my rectangle. Okay, continuing on, this will be 1/3. This integral would be, I was supposed to change to green. This will be x to the 3rd minus x squared, evaluated from 1 to 4, equals that magic height. Go ahead and take a second to finish out plugging in 4 minus plugging in 1. We should end up with 16 is my magic height. Now, if I wanted to know where does that magic height occur, right? This is the average value. This is what the question asked me for. Technically, I could stop here. But if you were curious to say, hey, what is c? You could take your function, evaluate it at c, and set it equal to that height and work backwards to figure out what input c gave me an output of 16. But again, not necessary, just pointing out that it would be possible. All right, so to summarize for you, the mean value theorem is the theorem itself, and it says that we have an cool calculus area is somehow equal to old average area, which if you think back to the mean value theorem for derivatives, we had that old boring slope was equal to cool new calculus slope. Okay, so what this is doing is it's relating something instantaneous or relating with those infinitesimally small collections of things and making it applicable to other concepts that we've studied in math for a long time. Okay, what's most important to take away from this is going to be this average value formula. Okay, you're going to see things like find the average velocity. So you do 1 over b minus a, the integral from a to b, velocity goes in here. Find the average acceleration. 1 over b minus a, integral from a to b, acceleration goes in there. Find the average temperature of the bath water, like one of those problems we've done before. 1 over b minus a, integral from a to b, bath temperature water. Whatever you're finding the average, bleh, as I often tell my students, the average value, the average f in this case, okay, is 1 over b minus a, the integral from a to b of that thing that you want the average of. Thanks for watching.